Hello learners, welcome to this course on Embedded System Design using AT89C51 microcontroller. In this tutorial, I will be discussing about how to transfer a temperature data to a PC using the serial port protocol. So the complete project and its code is available in the GitHub repository link which I show at the bottom. So let us start with the application of sending the temperature data to a PC. So we are going to make use of LM35 temperature sensor which can measure from a temperature range from minus 55 degrees centigrade to 150 degrees centigrade. It has an accuracy of about 0.5 degree, and for every 1 degree variation it can able to produce 10 millivolt as an output. For example, if the room temperature is 30 degrees, the sensor will produce an output of 300 millivolt. So it is a 3-pin IC where the pin number 1 will be your supply, pin number 3 will be your ground, and pin number 2 will be the analog voltage signal. So this analog voltage signal will vary with respect to the temperature. So we will be interfacing this LM35 IC to your AT89C51 microcontroller. Since AT89C51 microcontroller, it does not have a inbuilt A to D converter, we are going to use an external A to D converter IC which is ADC0808 IC. So this is an 8-bit A to D converter which converts your analog signal to a digital signal, and the digital signal will be given as an input to your microcontroller through this port 1. So we will be displaying the temperature value in an LCD connected to port 2, and also we will be sending this temperature data to your PC. So in order to send this temperature data to a PC, we will be making use of the inbuilt UART module in the microcontroller. So UART stands for Universal Asynchronous Receiver Transmitter, which is an asynchronous mode of communication where we use 3 lines: a transmitter line, a receiver line, and a ground line to transmit the data as well as to receive the data. So this transmitter line is multiplexed with your port 3.1 and receiver line is multiplexed with your port 3.0. When we look at the signal levels coming out of this UART from a microcontroller, in order to indicate a logic low, it will be 0 volt. To indicate a logic high, it will be 5 volt. Whereas in case of a PC, if I want to indicate the voltage ranges, like as logic 0 will be represented by a plus 12 volt and logic 1 will be represented by a minus 12 volt. So from this we can clearly see that there should be a voltage translation and also there should be a shifting of the voltage. So in case of microcontroller, logic 0 is represented by 0 volt, whereas in case of a PC, logic 0 is represented by plus 12 volt. For logic 1 in microcontroller, it is represented by plus 5 volt, and in case of a PC, it is represented by a minus 12 volt. So we should do a voltage level increase as well as there should be an inversion. For 0 volt, it should be translated to plus 12 volt. For 5 volt, it should be translated to minus 12 volt. On a similar note, if I want to send some data from PC to a microcontroller also, the reverse process should happen. So this will happen with the help of your IC called as MAX232 IC. So MAX232 IC will act like an intermediate between your microcontroller and the PC, which converts this voltage levels and also it changes the polarity of the voltage levels. So this MAX232 lines you can see here, this T1 in and R1 out can be connected to your microcontroller where we will be having this TTL logic. So TTL logic stands for transistor logic, where we have this voltage range. On the other side of your MAX232, you will be having a RS232 logic. So RS232 logic, in that you will be having the voltage ranges specified here. So we will be converting this voltage ranges, and in order to connect a PC with your MAX232, we will be using a DB9 connector. So the DB9 connector, it can be of male connector, it can be a female connector. In this we will be using importantly 3 lines. One is your transmitter line, receiver line and a ground line. Other lines are for handshake signals. So usually the pin number 2 will be a transmitter line, pin number 3 will be a receiver line, and pin number 5 will be a ground line. So thereby we connect our microcontroller with the computer with the help of a MAX232 driver. And another important point to note here is the data transmission happens in a packet format. So the packet of UART, how it is going to be? So the packet starting is indicated by a high to low transition, which indicates the start bit of a packet. And then we will be having a data, which can be 7 bits or 8 bits. And then we will be having a parity bit, and finally there will be a stop bit. So the stop bit indicates a low to high transition. So here the important thing is, in case of data, so first the LSB bit will be coming after your start bit, and finally your MSB bit of the data, it will be coming through your packet. So for example, if I take a letter M, its ASCII value is given as 1001101. In that case, if I want to transmit this data M using a UART protocol, first I will be having a high to low transition, which indicates a start bit. Then comes your LSB bit. Okay, LSB bit is 1. Then the subsequent LSB bit 0, 1, 1, 0, 0, 1. Then I am going to introduce a parity bit, which is an optional bit. So here we are trying to put it as an even parity. Even parity in the sense, in my data I am going to have even number of ones. So here I have 4 ones, which means it is an even parity. So even parity is indicated by a logic 0, odd parity is indicated by logic 1. Afterwards, the stop bit, where I will have a low to high transition. So this is the packet format through which the data will be communicated between the devices. The only difference is the voltage range is going to be changing. The high level voltage and low level voltage is going to change depending upon whether it is a microcontroller or it is a computer. Now let us look at the configuration part. Whenever I want to send the data using UART, we have to configure the UART. So for configuring the UART, we have to make use of certain registers. So the first register which we are going to configure is your SCON, serial control register. So here I am going to have the first 3 bits is for mode selection for the serial port. So SM0 and SM1 indicates serial port mode bit 0, serial port mode bit 1. So depending upon the combination which we take 00, 01, 10, 11, we can configure the UART in different speeds. For example, if my SM0 and SM1 is going to be 00, then our speed of data communication will be oscillator value divided by 12. So at this speed, the data will be transmitted. For example, if I am going to use a 12 megahertz crystal, okay, if I am going to use a 12 megahertz crystal, in that case what happens? 12 megahertz divided by 12, it will be equal to 1 megahertz. So 1 megahertz in the sense, it will be, a bit will be transmitted for every 1 microseconds. If I put a value of 01 to this SM0 and SM1, then we are going to configure serial mode 1. In that case, I am going to use a 8-bit UART. 8-bit UART in the sense our data is going to be 8 bits and the data rate is depending on your timer 1. Okay. How often the timer 1 overflows? Each and every time when the timer 1 overflows, a data will be sent out. So the speed of timer 1 overflow will indicate the baud rate, number of bits transmitted per second. Similarly, if I put 1 0, then it will be in serial mode 2, where I will be using a 9-bit UART. So 9-bit UART in the sense 9 data bits. So 8 bits can be in your buffer register. The 9th bit can be available in the serial control register, where this TB8 is the 9th bit of data transmission. Same way, if I am going to receive a data, the 9th bit will be coming to this RV8 position. And this REN stands for receiver enable. If the receiver should be activated, then this receiver enable bit should be 1. Then we have a transmission interrupt and a reception interrupt. Once the data is transmitted out, this transmission interrupt will change to 1. Same way, when a new data is received by the UART module, then receive interrupt will be 1. In case of SM0 and SM1 to be 1 1, then we will be having it in serial mode 3. Again, we have a 9-bit UART, but now the data rate depends upon the timer 1 overflow. Now let us look at a simple calculation. What should be the value for our timer 1, so that I achieve a baud rate of 9600. So let us take our SCON value to be 0x50, which means it is 0 1 0 1 0 0 0 0. So here you can see that I am going to put it as 0 1, SM0 and SM1 to be 0 1, which means I am going to operate in serial mode 1, where I will be having a 8-bit UART and the speed of transmission will be depending upon your timer 1. Now let us do some calculation. What should be the value I should load to this timer 1 register so that I achieve a baud rate of 9600. So let us assume we are going to connect a crystal frequency of 11.059 megahertz. So we have a formula to calculate the value which we need to load into the timer 1 register. So TH1 stands for the timer 1 higher register, which is a 8-bit register, which is equal to 256 minus crystal frequency divided by 384 divided by baud rate, where this baud rate is going to be your 9600. And this formula is applicable when I have PCON 7th bit is going to be 0. So here I show a PCON register where the 7th bit is for your serial port. Serial port configuration. If this bit is 0, then we make use of this equation. If this bit is 1, then we make use of this equation. So let us take this serial mod bit to be 0. In that case, I am going to apply this formula. So where TH1 equal to 256 minus this is 11.059 megahertz. So that I am writing in terms of a hertz divided by 384 divided by 9600. When we do the calculation, we find that the TH1 value which we need to load is 0xFD. So if I load this value into this TH1, then whenever the timer 1 overflows, a particular bit can be transmitted. A particular character can be transmitted. There are few more registers which we need to do a configuration, where I have this TCON register, timer control register, where this TF1 is going to indicate the flag for timer 1. Whenever the timer 1 overflows, this flag will be set. If the timer 1 is not overflowing, then this flag will be 0. Same way for timer 0, we have this flag. To enable the timer 1, right, to start the timer 1, we make use of this TR1. If this is 1, timer 1 will start its counting. Same way we have a run bit for your timer 0. So other bits are for your external interrupts. We will not go into the details of this. So here we are going to use this TCON and this TR1 bit to be 1, which means we are going to start the timer 1. using this bit. And another important register is your timer mode register. So the timer mode register is given here. We are going to make use of timer 1. We have to select the mode of operation. So the timer 1 can operate in 4 different modes. So this 4 bits is for configuring your timer 1 mode, where I have a gate bit, counter or timer mode. So 1 in the sense it will be in a counter mode, 0 means it will be in the timer mode. We are going to operate it in the timer mode. And M1, M0 determines which mode of operation. If it is 0, 0, then the timer 1 will be in a 13-bit timer mode. If it is 0, 1, it will be in a 16-bit timer mode. 1, 0 means 8-bit auto reload mode, and 1, 1 means split timer mode. So there is a separate tutorial on this timer configuration. Please have a look at it. So here for this application, I am going to use the timer 1 in a 8-bit auto reload mode. So I am going to put a value of 1, 0 here. So which means I am going to have 0, 0, 1, 0. This is 2, 0, 0. We are not going to use the timer 0, right? So our mode 1 and mode 0, I am going to set it as 1, 0. So 1, 0 means it is 8-bit auto reload mode. What is this 8-bit auto reload mode? So I have two registers, TLX and THX. So this is a lower register for timer 1 and this is a higher register for timer 1. So what we do is we put a value into this THX. Load a value into this THX. So this we have already calculated, that is going to be 0xFD. As soon as I load a value into this THX, this value will be going to your TLX. And this TLX will start incrementing its data, which depends upon the timer's overflow. Whenever timer overflows, the value will be incremented. So once I have this value 0xFD, when the timer 1 overflows, when this value gets incremented, what happens? It will go to 0xFE, then 0xFF, then it starts overflowing. When the overflow condition happens, automatically this flag will be set. Once this flag is set, data will be transmitted or received. Again what happens? We load the same value again into this THX. From THX it goes to TLX. Again the timer is running, and when it overflows, again the flag will be set. So this process continues. So this type of mode is called as a 8-bit timer or counter in a auto reload mode, which is used for determining the speed of your data transmission. So now let us look at the application where we will be sending the temperature data to your LCD as well as the PC. So here I have oscillator circuit where I have connected a 11.0952 MHz crystal to the microcontroller, and there is a reset circuit as well, and we have a temperature sensor LM35 temperature sensor, and this LM35 data is connected to the IN0 channel of your ADC0808 IC. This is a 8-bit ADC IC. To select a particular channel, we have to configure the address using this address A, B and C. So by giving 000, the IN0 channel will be selected and it will be converted into a digital data, and the digital data will be available through this out1 to out8, where out1 will have the MSB and out8 will have the LSB of the 8-bit data. To indicate this address A, address B and address C as an address, we make use of ALE, address latch enable bit. So this should be set to 1. so that this ABC will be treated as an address. Then in order for the ADC to work, we have to give a reference voltage. So I am going to give a 5 volt as a reference voltage. If I give 5 volt as a reference voltage, then the resolution of the ADC will be about 19.61 millivolt. How we get this? We get this using V reference divided by 2 power n minus 1. So V reference is your 5 volt divided by n is nothing but 8. So it will be 2 power 8 minus 1. When we do this calculation, our resolution will be about 19.61 millivolt. So this is the smallest voltage change which can be represented in a proper binary bit pattern. That determines the resolution of your ADC. Next, we have few control lines like start the conversion process, end of conversion. So the start the conversion process should be given by the microcontroller to initiate the conversion process. Once the conversion is complete, the ADC chip will give an indication through this end of conversion process. In order for the conversion to take place, we have to give a clock frequency. Usually this clock frequency will be of about 500 kilohertz. And to get the converted result as an output through this out1 to out8, we will make use of this output enable line. When this output enable line is on, the data will appear through this out1 to out8. And this data is connected to your port 1 of your microcontroller. And this data is displayed in your LCD connected to your port 2.2 to 2.7. And also this data is sent to your computer to this virtual terminal through this MAX232 IC, where we make use of this transmitter line and receiver line is connected to your T1 in and R1 out of your MAX232, and the output of your MAX232 T1 out and R1 in is connected to the virtual terminal. So this virtual terminal is similar to that of your PC. So on the left side we will have a TTL logic, on the right side we will have a RS232 logic. So now let us look at the programming part. As I said earlier, the computation of ADC resolution, which is done by this V reference divided by 2 power n minus 1. If I take 5 volt as a reference voltage, I can write in terms of 5000 millivolt divided by 2 power 8 minus 1. Then the resolution will be about 19.61 millivolt. For example, if I get a ADC value of 00001111, then to compute the measured voltage, I will multiply this 15 with 19.61 millivolt. So I get about 294.15 millivolt. This is a voltage, but we need to convert it into a temperature. So to convert it into temperature, we already know that for every 1 degree centigrade, I will get 10 millivolt as a variation from our LM35 IC. So what we do, we divide this voltage by 10 to get the temperature value. Now let us look at the programming part. So here we have a LCD connections. So where the RS pin of your LCD is connected to 2.2, enable line is connected to 2.3, D4 is connected to 2.4, D5 is connected to 2.5, D6 is connected to 2.6, D7 is connected to 2.7. So we are going to use the LCD in a 4-bit mode. Then we initialize few variables like ADC underscore RD to get the ADC data, 8-bit data. Then I am going to convert this ADC data into a string. So that string will be available in the temperature variable, and we are going to use another variable called as temp. And I am going to write a small subroutine to send the data. So this is a small subroutine to send the data. So for example, I have something like 29 to be sent. So this will be available in a string format. So the first address of this first character will come to this subroutine, and when I have this data, what I do, I put the data into the serial buffer, and this data should be transmitted out. So until I transmit the data, my TI will be 0. TI stands for transmission interrupt. So transmission interrupt will be 0 when the data is in the process of transmitting. When transmission interrupt changes to 1, which means the data has been shifted out. Data has been shifted out. So until I shift the data, until I shift the data, this bit will be 0. So I am keep on continuing here. Once this TI bit goes to 1, we will be coming out of this loop, and we will make the TI to be 0 again, and again it goes into this loop again. So then the 9 will be shifted out. So like this, the transmission is going to happen using your UART terminal. So let me explain it one more time. So if I want to transmit the data, what I am going to do? I am going to put the data into the serial buffer. From serial buffer, the data will be shifted out. Until the shifting is going on, my TI bit will be 0. Okay, so I am going to wait here until my shifting is done. Once the shifting is complete from the serial buffer, then what happens? TI will change to 1. In that case, I will come out of the loop, and again I will set the TI value to be 0. Again, since more characters needs to be sent, again it will go to this while loop. Again the next data will come to the serial buffer. Until it is shifted out, I will be here itself. Once that new data has been shifted out, again I will make it to 0, and again I will continue until the end of my string. So that is how the data is sent from your microcontroller to the other devices through your UART terminal. So now let us start with the main program. So where I have this serial control is set with 0x50, which means I am going to configure the UART, and its baud rate is set by the timer 1 overflow. And tmod is set with 0x20, which means timer 1 is configured in a auto reload mode. And already I have set th1 and tl1, I am going to set it with 0xfd, which is going to indicate I am going to have a baud rate of 9600 bps. Then I am going to start the timer. Then we need to configure the ports. So port 1 is configured as an input because I am going to get the 8-bit data. The converted 8-bit data from your ADC IC, it will come to this port 1. So it is configured as an input port by setting it as 0xff. A particular pin, if it is set as 1, it will be configured as input. If it is set as 0, it will be configured as output. For port 3.2, 3.3 and 3.4, I am going to use it for A, B and C. Right? So this will be configured as an output. And 3.5, I am going to use it for ALE, and this also will be configured as an output. So after configuring this bits, I should also configure your output enable bit and start the conversion process. So that is available in your 3.6 and 3.7. So both will be configured as output lines. Once the ports are being configured, right, we have to set the values. For setting up the values, port 3.2, 3.3 and 3.4 is set with an address of 000, which indicates IN0 will be selected. To indicate this is an address, we will make 3.5, which is a ALE bit. So ALE bit is set to 1. And we also configure the end of conversion line. So end of conversion line, once the conversion is complete by the 8-bit ADC, it will give an indication. So that indication comes to your microcontroller as an input. So this port 2.0 line is used as an end of conversion bit, and it is configured as an input bit. Then what I am going to do, I am going to send a string using the UART module. So temperature equal to, so this will be sent to the PC. wait for some 500 millisecond, then I am going to initialize my LCD. Then in a while loop, what I do, ADC underscore RD, I am setting it to 0, initializing it to 0. Then I say that start the conversion process. So SOC is equal to 1. After some 1 second, I am making this SOC to be 0. Right? Once the conversion is complete, this port 2.0 will be set with 0, because our end of conversion line is connected with a NOT gate. Here you can see the end of conversion line is connected with a NOT gate. So this EOC will be 1 once the conversion is complete, and I am inverting it and I am giving the 0 to this port 2.0, which means we have to detect whether our port 2.0 is 0 or not. If it is 0, then the conversion is complete. That is what we indicate here. Right? So we try to check whether our end of conversion signal has been generated. Once it is done, I am enabling the output. So output enable is set to 1. Then I am reading the data from port 1, moving it to the variable ADC underscore RD. Then this value should be converted into a voltage. So to convert it into a voltage, I take this value, multiply it with the resolution of your ADC. So this gives the voltage value. And in order to convert my voltage value into temperature, what I have to do? I have to divide it by 10, because for every 1 degree centigrade, our sensor will give a 10 millivolt variation. So I am going to divide this voltage by 10 so that I get a temperature data. So this temperature data is converted into a string using this int to string function. And then in a LCD, I am going to display this first row, first position, temperature. In second row, first position, I am going to display in C equal to. Then I am going to put this temperature, whatever the string data which I get after conversion process, so that I am going to display it in a LCD. And also I am going to move the data to a UART terminal. After moving the temperature data, I am going to send a string C to that, so that it will be temperature equal to value string. And this process is going to continue infinite number of times, since it is enclosed in a while of 1. So that is how a data from the temperature sensor is displayed in a PC as well as in a LCD. So now let us look at the programming part and the circuit part. So here I show a typical circuit. So here you can see that we have a temperature sensor connected to your ADC 0808 IC, and this output is connected to your port 1 of your microcontroller. We have an oscillator circuit here, we have a reset circuit here, and we have the control lines connected here. A, B, C, ALE, output enable, start the conversion process, and the end of conversion is connected to port 2.0. And LCD is connected to port 2.2 to 2.7. This port 3.0 and 3.1 UART lines are connected to your max 232, and from that max 232 it goes to a virtual terminal. So this is a typical circuit which we build. Now let us look at the programming part. So this programming is done using your Micro C Pro for AT51, where we have written the code which I have explained just now. Once the code is written, I have to compile this code. We use a build option. So to convert your embedded C program into a hexadecimal file. Once it is converted, I go to that circuit which we built using Proteus 8 Professional. So here I have to dump that code, right click on the microcontroller, go to edit properties, put the corresponding clock frequency and select the hexadecimal file. So you can see the hexadecimal file here. Import that file into your microcontroller. Press OK. Once the code has been dumped into the microcontroller, we have to run it and we have to check the result. So to check the result, run the simulation. So you can see this is a virtual terminal where it is displaying 47 degrees and the same value is displayed in your LCD also. Now when I start varying the temperature sensor values, okay, so let me keep something like 35 degrees. You can see that it is getting varied. You can see the temperature gets changed. So similarly, if I vary still the temperature, something like 28 degrees, you can see that it is automatically getting varied in your virtual terminal. Virtual terminal is something similar to that of your PC, and the corresponding temperature change you can also see it in the LCD. So this is how a simple temperature data can be measured and it can be displayed in a LCD as well as in your PC. So we can create some GUIs. We can create some GUIs using VB or using Python. We can create a GUI to read this data from your sensor, and this data can be displayed in that particular GUI. So in this tutorial, I talked about how to measure LM35 data and how to display it in a LCD and in a PC. The complete code and simulation of the project is available in the GitHub repository link which I give below. Thanks for watching. Please subscribe for more technical learning. Thank you.